So how might this work? Let's check out this animated demo. So in this demo, we're going to start with the exact heap we had in the question. We're going to insert 3. So the way to think about this, and maybe you can just watch only this part, and this may give you a clue, is we want to first and foremost ensure that our tree is still a heap when it's done. So in other words, we need it to be a, first of all, complete tree, and second, we need it to be a min heap. So in order to ensure completeness, we could just throw our item in here. Okay? And at that point, if we look at this tree, if we think about its heap properties, it has the completeness property, but it is missing the min heap property. So we need to fix that. So if you didn't quite figure it out before, maybe pause this video and figure out what happens next. But in this case, we can look at this and we could say, what's wrong? Well, 3 is not in the right place, right? 5 is greater than 3, so 3 should be up higher. And so what we can do actually is say, 3, you should move up. You should climb the tree to your rightful place. This is not for you. You're greater than this. So we swim up the tree. Sometimes the word swim is used, and swap with 5. So 3 is better now. If we think about this, this is a little tiny heap. This is a recursive data structure, but the global structure is not a heap. In particular, this right here, starting at 5, is not a heap, and so we need to move this 3 up even higher. So we move 3 up, and at this point, we have guaranteed that this whole thing over here is a heap, right? We don't have to think about this left side. That's an important point. And the reason we don't need to think about it is that 5, which used to be there, is less than 6. And so when 3 takes its place, it is also going to be less than this left tree. So in other words, we can climb up greedily and end up in our correct place. Now at this point, 3 says this is my true place. Good. So suppose we add another number, let's say 5. Well, in this case, the end of the heap is now here, right? It's not down here somewhere. It's going to be here. And 5, in this case, is not in its right place. So we'll climb up until we find our correct place. Okay? So we go up and we find ourselves home. For the first time in our lives, finally home. Now let's think about the deletion operation. And again, if you didn't quite figure it out before, it might be worth pausing this video to think about how you do this. So again, we're going to take advantage of this idea that we want it to always be complete. That's a constraint. It makes our lives easier. So I have to delete the minimum operation item, which is here. And so if I wanted to somehow preserve completeness, maybe the most natural thing to do is to take the last item and just stick it in the root, right? So, deleted. And then 6 finds itself transported magically into the top level. Now, of course, 6 is very unlikely to actually be a great new root. In fact, it might be impossible. Is it always impossible? Not certain. Anyway, but at this point, 6 says, I'm definitely not cut out for this. I'm like a lowly person on the totem pole. I should not be in charge of the whole tree. And so the person below says, get out of here. So 6 will now sink, and you'll basically sink your way down the hierarchy, yielding to the most qualified folks in your heap. Here, 6 is still not quite in the right place. And so finally, 6 is like, phew, that's good. If we delete again, now 1 goes away. 5 is now going to get thrown into the wolves in charge of the whole thing. In this case, we actually have a tie. So if we're going to sync, we can actually just break the tie totally arbitrarily. It doesn't matter. So let's say I go left. And then 5 will basically say, I'm not going to descend further. I found my right place. So I happen to get thrown into the root of the whole tree. And now when I sync, I'm going to go down until I found my place. Okay? And so that's that. So in other words, we could think about the whole heap process as the following, right? So given a heap, how do we implement the priority queue? Get smallest, we return the item in the root node. Add, we can think of it like a company, right? So you can imagine that X is a new employee. You place the new employee in the last position, and you'll promote them as high as possible. So you stick them down in the low-level, factory floor job, and then you see how high they can go. In remove smallest, you basically assassinate the president of the company, promote the rightmost person in the company to president, whoever that person is. So you go to the bottom of the org chart and you're just like, okay, the last department on the list is, let's say, just arbitrarily gardening. Okay, so among all the landscaping folks, who's the lowest person on the totem pole there? Okay, it's the guy that bites the twigs. Okay, well, we'll take the twig biting guy, put him in charge of the company, and then we'll just demote that person repeatedly until you find yourself in the appropriate location. And when you do the demotion, a really important thing is you have 2 basically vice presidents. You pick the stronger of the 2 vice presidents. And so there's a remaining question, which is how can we do this all this in Java? And well, we'll talk about that a little bit in these next little bits. But before we do that, we have to think carefully about how trees could be represented in Java.